let's look at a few chemical reactions and the calculations that we can do to figure out how much reactant is needed to produce a certain amount of product, or how much product is produced given the amount of reactant that we're using, and those kinds of things. So in subsequent series of videos, we're going to be looking at a theoretical yield and limiting reactant and percent yield. Let's consider this question. We want to know how much CO2 is given off per gallon of gasoline burned. We're going to have to make a few assumptions. So gasoline is a mixture of hydrocarbons. Let's assume that gasoline is purely octane. Octane is C8H18. And in a combustion reaction, we know that we will also need oxygen. So oxygen is going to come in here. And as products, we produce CO2 and water. So I'm just going to write my reaction up here. And we will see where it takes us. So remember that the first step to doing reaction calculations is that we need to start with a balanced chemical equation. So here we go. We would start balancing with the elements that appear in the fewest number of compounds, so that would be carbon or hydrogen. So let's just start with carbon. So we have 8 here, and so we'd need 8 here. Then we have 18 hydrogens, so I'd need 9 waters. And then let's check my oxygens. So I only have 2 on the reactant side, and now that I've done this, I have 16 oxygens here, plus 9 is 25. So I could say this is 25 over 2. Then, in order to get this into the smallest whole number ratios, we would multiply everything by 2. So I'd end up with 2, 25, (16) and 18. So before we even dive into calculating, we know that for every 2 moles of octane, I'm going to produce 16 moles of CO2. So that's a pretty big ratio there, CO2 to octane. I have my table built here so that I can fill in the information that I need. And you don't have to use the table, and we certainly won't fill out all of the information in the table because we won't need it all, but it's nice to organize the data that you have and then fill in the boxes that you need to work your way to the answer that is asked for. In our first row here, we're going to have initial mass, or we could have volumes. It just depends what's given. We know that ultimately we need to get on that mole train. So we need to go from whatever is given, be it mass or volume, to get to moles. My question again is, how much CO2 is produced per 1 gallon of gasoline burned? Since we're talking about a pure substance, octane, we can use this volume and use the density to get a mass. So we have 1 gallon, and we were told that 1 gallon is equal to 3.97 liters. So we'll end up with liters out of that. And then using the density, we can get the mass. The density is given as 0.692 grams per milliliter. And the milliliters will not cancel with the liters directly, so we need to throw in another conversion here where there's 1,000 milliliters and 1 liter. So now my liters cancel, my mils cancel, and I'm left with a final unit of grams. And if we do this calculation, we end up getting 2,623 grams of octane, C8H18. So we'll go ahead and put that number into our mass block up here. Now, if we're burning this gasoline in air, there's going to be an excess of oxygen. And so the amount of O2 is not relevant for us. We'll look at calculations down the road where we won't have an excess of one reagent, and we'll need to do a calculation in order to determine what is known as the limiting reactant. More on that later. Now that we have our mass, we need to get on that mole train. So we need to know the molecular weight. The molecular weight, if we add up the mass of all the carbon and hydrogen, is 114.22 grams per mole. And if we do the calculation now, 2,623 grams, using this mass, we would divide that to get moles, and we are left with 22.97 moles. And we would plug that into here, 22.97 moles of octane. And so then we would say, well, if all of this is going to be burned, all of this is going to be consumed, and we would be left with 0 moles of octane at the end of my chemical reaction. And we want to know the final mass. We want to know how much CO2 is released. Now that we're on the mole train, we can use the mole ratios in my chemical reaction to determine the moles of my product that's going to be produced. So I have 22.97 moles of C8H18. I get my mole ratio from the balanced chemical equation. I have 2 moles of C8H18 and producing 16 moles of CO2. So I would get 183.7 moles of CO2 out. So I would make 183.7 moles of CO2 from this reaction, giving me 183.7 moles at the end of my reaction, because I was starting with 0, as is the case most of the time when we're talking about a chemical reaction. Then we need to go from moles to kilograms, as the answer is asked. So we have 183.7 moles of CO2. The mass of CO2, which we could plug in here, 44 grams per mole. Notice I didn't plug this in at the beginning because I'm actually not going to need masses for these other things. I'm not going to waste my time doing that until I need it. 44 grams per 1 mole. So we have mass of CO2, it's 8,087 grams. And then to go to kilograms, there are 1,000 grams in 1 kilogram, so we get 8.09 kilograms of CO2. So that's a pretty significant amount. That's about 16 pounds of CO2. To recap the steps, we balanced the chemical equation, we gathered the data that we were given into a table, we got on that mole train, used the mole ratios, and then solved for the final answer in kilograms. Thanks for watching.